Hey again, everyone. Now that we're done talking about the grand machine, it's time to get started on a very important mathematical concept for any kind of relation. We've already talked about relations in the last lesson, but you're probably wondering, have we seen any? Yes, we have seen relations so far, of the linear persuasion. We will be seeing some other ones, mostly graphically here. I'm not holding you responsible for any kinds of equations for relations just yet. But as the year goes on, we'll probably be seeing a lot more of them, namely the kinds that are quadratic and exponential. But again, detail, and we're probably not going to see those until the end of the year. However, before we understand that, we need to understand a concept of domain and range. And no, domain is not the name of the fancy mansion you live under, and range is not the football field that you're practicing throwing your ball in. Instead, these have a different mathematical definition. But for starters, let's talk a little bit about what all these terms mean. Any mathematical relation sorry, no, not relation, machine, apologies. Any mathematical machine, which we call in parentheses relation, sticking with the grand machine analogy. I hope that you all drew the machine in detail, otherwise you know what's coming after you. Each one has inputs, what we give it, and outputs. And in blue, outputs. In other words, what we get in return. What we get in return. These forms of inputs and outputs can easily be translated into more or less what we call domain and range. So the inputs are called the domain or the x values that a relation can possibly take. While the outputs are called the range. Or you can probably guess based on the previous sentence, or the y values. That a relation can possibly take. So this seems a bit abstract so far, but let's try to dissect this bit by bit. We're talking about the x values and the y values that a relation can possibly take. In some cases, you may be wondering, what are situations where they end up anything too weird? But let's see that in a moment. But real quick, side note, almost all the time, the x's are the domain, the y's are the range. There are some exceptions, but we don't see those in Algebra 1. That's why I'm kind of generalizing it to this for right now. It just makes things easier for us. But in Algebra 2, you'll probably see some other kinds of examples where the inputs and outputs don't exactly work that way. All right? For instance, let's talk about the relations that we've already seen so far. So for instance, let's look at linear relations. This is how we're going to see in detail what we're talking about when it comes to how we know what x values we can take and what y values you can take. But one thing to quickly recall is that straight lines, or like any kind of line that we know of when we're plotting it, unless we specify otherwise, is going on and on forever in the direction that we want it to go. All right, so there's that, and let's draw this green line up here that's going horizontally. And I'm going to say that it's passing through 3 at about right here. That'll be important for later. That's why I'm specifying it. Okay? So, If you look at these lines very closely, namely the blue and the red lines, what possible x values can they take? If you look at it, it goes on forever from left to right. Is there a single x value in terms of real numbers that it's not going to take? Well, if we go on forever, no, not really. It's just going to go on and on forever, and every single x value will be possible. Same goes for the red one. It may be decreasing, but it's still the same logic. It goes on forever and ever, and ultimately every single x value is possible. And we know this when it comes to solving linear equations. Like if you had something like y equals, say, negative 2x plus 3 for the red line, you could fill in x and y with just about any real value, and we're not going to have any problems with that. Again, we'll be looking at these things more so graphically here because we haven't really talked about any relations outside of linear. But I hope you're seeing the point at this point, that no matter what, as far as we go, we could go on forever and ever and ever and ever and ever and ever, and every single x value can be taken. But we've been talking a lot about the domain. How about the range? For both the red and the blue line. Is there a y value that we can't possibly take? Well, the way I'm looking at it, it doesn't look like it's skipping any values. So at the end of the day, no, there's no value it can't take. So I guess the question you're asking now is, how do you represent this? So let's talk about the red and blue lines. The way that we're going to represent this in terms of answers, let's go a little bit more in detail here. What x values can they take? In this case, the answer is all real numbers, or if we like to represent it as a single symbol, so we're not writing all real numbers all the time, it's this fancy looking R. Think of it as sort of like a longer bar for like the side of the R, but it's like this. The way you draw it, if you want to draw an R normally, and then draw like a line passing through here, kind of like at the crossover from like the ovalish part and then the arm that the R has, that's what it looks like. This means all real numbers. It is a shortcut that I will allow you to use whenever we're writing domain and range. It's actually preferable in math, so ups to you if you can do that. Similarly in questions, what y values can they take? Once again, as we specified, it's also all real numbers, or R. So, the way we represent, you don't have to write all in detail. The way we represent this, more so properly the way we represent it, is as follows. D and R, proper R this time, not the fancy R that we were just using for all real numbers. That's reserved for being extra fancy right there, which is reserved for all real numbers. So here, D is all real numbers, R is all real numbers. Remember that D is for the domain, R is for the range. And it's as simple as that whenever I ask you for domain and range. Just say that D equals whatever they are, and R is whatever numbers they are. Okay? But we still have one more case we need to look at here with this one. The green line. So again, when it comes to sketching this out, I just want to say that I don't care about the specificity, except with the green line. And if you want to name them in any which way so you don't get confused, let's call the blue one F, the red one G, and the green one H. Notice here that things have changed. First of all, can anyone tell me what equation this straight line takes on? We have the information to do it. Remember, it's a horizontal line, so it's always going to be in the form of y equals a number. And what's that number always going to be? 3. So y equals 3. If you want to think of it in terms of slope, note that we're never rising but always running, so our slope is 0. And our y-intercept is 3, so y equals 3. And I ask you again a similar question. What possible x values can we take? Well, in this case, we can still take every single one, because h will go on forever and ever 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 and ever. But how about the y values? In this case, it can only take on one single y value, and that y value is 3. So let's go into detail with this. How about the green line? It can still take all x values, but it can only take on one y value. That y value is 3. So how do we represent it when it's only one singular value? Well, let's represent it. First of all, the domain is still all real numbers. And the range this time, since it's only one singular value, what we do is we create curly brackets that look something like this. And in those curly brackets, we list every possible value that this function, or this relation, can take. In this case, the only one possible is 3. This is important, and I'm going to put a reminder, use the curly brackets. In mathematics, we're especially picky when it comes to talking about domain and range. So much so to the point that if you were to put that r equals 3 with no brackets, it would mean something completely different than if you put it with the brackets. And let's get in good mathematical practice. I know my Algebros can do it. So, with that in mind, I want to give you a couple more examples before I let you loose into the wild. All right, so now we have more examples. Again, do your best to sketch these as best as you can. I'm not going to really be picky about this, as in most homework assignments and the test, you'll have these more specifically drawn out, so it's not going to be a big deal. All right, so here we have a simple curve like this, cutting here at 1. We've got a funny little W right here, cutting at -2. It does actually touch -2. Let's be specific about that. And finally, we've got this oval right here. In mathematics, we call this an ellipse, stopping at 2, -2, and then here, -3, +3. All of these are relations, so the instructions here are to find the domain and range. So here, we want D equals, R equals, D equals, R equals, D equals, and R equals. All right, so let's start off with the very first one. This little curve right here that is going upwards. If you look at it, remember, if something is cut off by the confines of the graph, it's still going on infinitely. And here, with this one, it'll still go on no matter what. Like, we can take on any x value and we're going in either which direction. It's kind of hard to see when we only have such a limited scope, but you do have to envision that this is going on forever, okay? And with that in mind, it's still very much possible for us to give any x value here. So in this case, the domain is nothing more than R. The range, though, is something that we can see a little bit more clearly. Notice that the function, or the relation, I'm mixing that up a lot, even though in this case it technically is a function, but we'll get there. Shush. In this case, we never go below 1 in terms of the y values. As in here, we never go below this. So in this case, can we say that it's all real numbers for our range or our y values? No. How do we represent something like this now? Of course, we're not going to list out every single number from 1 on to infinity. What we can do instead is in curly brackets still. We can use an inequality in order to denote this. So in this case, we know that the y values can be anything greater than 1. So it's 1 and everything bigger than that. So I can say here in the curly brackets that y is greater than or equal to 1, which is basically what I just said right there. I just wrote it in math speak. Keep in mind this symbol is the greater or equal sign. In case anyone has needs a refresher, this sign means greater or equal. This sign is just strictly greater. meaning it doesn't include the value that we're talking about. Similarly, less or equal. And this one is strictly less. Just as a little bit of a reminder in case you don't remember much about your inequality signs. Okay? Now, for the next one, real quick. Notice the x values that we have a stopping point right here at that dotted line. So that's kind of like a stopping point. We're not going anything to the left of -2. So if you think about it logically right here, the x value can never be more than -2. So here, x can only be greater than or equal to -2. And the range. Is there any restrictions on the range? No, I don't see any. I don't see us getting stopped anywhere. So in this case, we know that our range can be any real number. So in this case, this is a case where the range is R. All right. I may be going really quickly, but once we hit the classroom and actually hit the books, we'll be talking about this in a lot more detail. Okay? Just know that whenever I have a dotted line like this or a line like this one right here, any lines like this mean that it's a restriction. We're not going beyond that. Okay? Let's talk about that oval, the curve, the curvy thing, the ellipse on the right. Let me ask you this question. What are the restrictions for the x values on the horizontal axis? Keep in mind the horizontal one is the one that's going left to right. Yup. It's the -3 and the 3. That's our restriction right there. So when we talk about our domain, we might have something a little bit more complicated right here. But it is worth practicing. In this case right here, it's our endpoints are -3 and 3, right? So the way we write something like this, again, instead of listing out every single real number between -3 and 3, we'll never do that. Put them as the endpoints right here on the sides, -3 and 3. In the middle, you're going to put x, and separating those, it's going to be the less than or equal signs. What such a notation is telling us is that x is between -3 and 3. And a similar notation can be used for the y's, because as you can tell, is a very similar case with the 2 and the -2. So here, instead of x, we're going to put y in the middle. And here, our endpoints are -2 and 2. Make sure you start with the smaller point on the left and the larger one, the bigger one, on the right. Otherwise, it wouldn't make sense. Wouldn't make sense to say that 2 is less than -2, right? Nah. Don't you dare put that on my tests. I'll stick a bunch of algebra fairies on you. And now for the U-try. If I can write. We've gone on for a while. And if you want to take a brain break, I totally get it. But for right now, let's give you a couple more examples right here. This curve right here does come with an extra note, and I'll get to that in a moment. But here's -4, and here's 4. It actually does touch here. I did this really badly. Let me redraw the last one. There is a note for the last one, so don't rush away yet. So for the last one, we are approaching the axes, as in the x and y axes, but never touch them. These might be tricky, but I do encourage you to give them a try, and we'll talk about them next time in class. And hey, maybe you'll get them. These might not be as hard as you think. I'll see you then.